How to calculate fundamental deviation in engineering design. Imagine designing a machine where parts must fit perfectly every time. How do engineers ensure that? The secret lies in understanding fundamental deviation. Let's explore how to calculate it step by step. First, think about the basic size. That is the nominal measurement of a part, like a shaft or a hole, before any manufacturing tolerances are added. Deviations are how much the actual part size can differ from this basic size. The upper deviation is the maximum allowed size difference above the basic size, while the lower deviation is the smallest allowed size below it. Next, identify if your component is a hole or a shaft. For holes, deviations are marked with capital letters from A to ZC. For shafts, lowercase letters from A to ZC are used. This helps in standardizing how deviations are assigned and calculated. Now, to find the fundamental deviation, you need to consult standard tables or use formulas based on the component size. For example, if you have a shaft with a size of less than or equal to 120 millimeters, and it is designated as with a certain standard, the upper deviation might be calculated using a formula like -265 plus 1.32 times the size, all in microns. Once you have the upper deviation, the lower deviation can be found by subtracting the tolerance grade, which is a measure of the total permissible variation, from the upper deviation. This gives you a clear picture of how much the part can deviate from the basic size in either direction. Applying these deviations helps in setting the limits of the tolerance zone. For example, in a hole basis system, the hole size is fixed, and the shaft size varies within the limits set by the fundamental deviation. This ensures the right fit, whether it's a clearance fit, transition fit, or an interference fit. In practical terms, calculating the fundamental deviation allows engineers to specify manufacturing tolerances precisely. When designing mating parts like shafts and holes, knowing these deviations ensures they will fit together properly during assembly. For example, if you have a hole with a designation H7 and a shaft with G6, calculating their fundamental deviations and tolerances will tell you if the fit will be loose, tight, or somewhere in between. To sum it up, start by identifying whether your part is a hole or a shaft, then use standard tables or formulas based on the size and designation. Calculate the upper deviation first, then find the lower deviation by subtracting the tolerance grade. Use these values to position the tolerance zone relative to the basic size, which guides you in designing parts that fit together perfectly. This process is essential in mechanical engineering to create reliable, well-fitting components that work smoothly in any machine.